record to this computer. All right. So, answers for exam one, I just recorded the video. I'm going to release those correct answers later today. Thank you very much for that question as well. So, that will be posted before the end of the day. So you'll get those answer options and you'll see, and I'll also post a video where I walk through everything. It's kind of confirmation of everything. Now, in the meantime, what we are going to talk about today is we are going to be looking at amino acids. But before we do that, I'm going to do my first top hat question. So you can answer your questions through the Top Hat app, which the question has not been posted yet, or it hasn't been kind of released. But here we go. Ask me later if I want to share these or if I want to recommend to a friend. Um, the course code, I don't believe that you need a course code. I think that you should just be able to go to um, Top Hat 300538, if that helps at all. Um, but I believe if you go through Canvas, that will help you out. The app will ask for a code, the Canvas auto. Okay, thanks, Andrew. Okay, so we are going to assign first question. And okay, this current is start presentation. There we go. Okay, let's go through Canvas. Okay, cool. All right, so first question. The concentration of hydronium ions, and this is really background sort of stuff. Okay, there we go. Let's go ahead and answer that first question. Does everyone uh, question should be up? Okay, I've got one answer. I'm sharing that screen. Okay, good. Good, 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 good. I usually like to give about 30, 45 seconds to answer, but also look at how many people are responding. Okay, I'll give about 10 more seconds. And done. Okay, so our responses for this one, we had 48% say that this is a true statement, and it absolutely is a true statement. So I'm not seeing the question pop up in my top hat. Not really sure what to tell you about that. We can, if you we'll have a couple more questions, so hopefully those will pop up, and it's just something, uh, I don't know exactly what, but a little bit of a delay there. So this is like a fundamental thing about, or this is fundamental to understanding like solutions and solution chemistry. And what we're going to be working on is we're talking about amino acids. Now, our learning objectives for today is we want to get through um, amino acid classification, nomenclature, and their structures, as well as ionization of amino acids. Okay, so the first thing that we want to do is we want to use two different molecules, acetic acid and ammonium, as our kind of, I guess, foils or as our models. Now, these are two molecules that are um, um, just a second. These are two molecules that are really important for basically your understanding of ionization. And so what we're going to do is look at these two different molecules. One of them, as you can see, is neutral. That's our acetic acid. And then the other one is ammonium. Now, an important distinction is there's different names for these. Acetic acid, whenever it's in its ion form, is acetate. Ammonium, whenever it's not in its ionic form, is ammonia. So you gain and lose a proton. So here's a model of what that is. And our pKa of 4.8 is the pH where we have 50% of each one of these molecules. So these two different forms of this molecule, one's deprotonated and one's positive. Sorry, one's deprotonated and negatively charged, and one's protonated and neutral. Now, when we look at that, we have we can put together a titration curve. Now, this titration curve is a very simple model of a titration curve, but it hits on the high points and the relevant parts of this for this class. So whenever we look at a titration curve and we see basically our two different forms of our molecule, we've got, I didn't see that pop up on my, okay. Okay, well, the top hat questions, they will sort themselves out over the course of the semester. Okay, so this is just our first run at it. And we're going to be all right. So this form of our molecule and this form of our molecule, the term that I want you to become very familiar with is predominant. So the predominant form, or sorry, this form of our molecule, our protonated form of the molecule, predominates on this side of our titration curve. And this is the predominant form on this side of our titration curve. So basically at a higher pH, we have this, and at a lower pH, we have that as our most common form of the molecule. Now, with that said, got another top hat question. So for those of you who were unable to answer the first question, let's go ahead and see if this one works. And this one should give you multiple answer options. Right now, I've got, okay, so one person's answered. And it looks like in the event that it's not working on your app, you can text 9174 plus your response to 315-636-0905. I've never done that, but I've called into Zoom meetings and that's similar functionality is good there. So all of the possible charges, whenever I say like acetic acid, I mean acetic acid and also consider acetate. What are the possible charges of that molecule or of those molecules? I'm going to put the 60-second timer on. Got 43 responses, 48. Can we get all 58? I think we can. Two, three, we got five people, four people left. Okay, you could uh, potentially try texting, but we've got more questions, so we'll get them on the next one. Three left. Okay, time is up. Okay, so we had, this was a little bit tricky because we have multiple responses, but our correct answers for this molecule are -1 and 0. Now, a question that I always like to ask is, can acetic acid adopt a positive charge? No. Can acetic acid be protonated? Absolutely. But can it adopt a positive charge? No, it's not going to. Now, with that, let's go back and look at another molecule. So we've got acetic acid that is going to oscillate between negatively charged and neutral. We've got ammonium. that will basically go back and forth between positively charged and neutral. So the protonation state, hi, can I get a number, get the number for the submissions I couldn't submit? And yes, I will post that into the chat next time. Um, so we've got all of these other molecules that have, sorry, we have a molecule that's going to either be positively charged or neutral or negatively charged or neutral. Now, a titration curve for something like ammonium is going to look largely the same, but it's going to be a little bit higher on that pH curve. These are both monoprotic molecules, so they both gain or lose a single proton. Now, I like to bring those up because when we look at the backbone of an amino acid, we have our amino group and we have our carboxylic acid. So these two parts of the amino acid are super relevant to, well, what constitutes an amino acid. In fact, I always like the term amino acid because it tells you what you're talking about. You've got an amino molecule or an amino group, and then you have an acidic group. And I think that remembering that is helpful whenever you're learning the structures of our amino acids. For instance, we have two amino acids, which we'll get to in just a little while, and those are aspartic acid and glutamic acid. What type of functional group do you think that those have? Well, we've got a carboxylic acid. So when you think about amino acids, I would think about acidic almost always means, well, an aspartic acid. Now, every single amino acid is going to have a backbone that looks this exact same way. It's going to have pKa's that are one low and one high. When this molecule gets deprotonated, it's going to first get deprotonated. If you're starting from a very acidic environment like this, you're going to lose a proton from the C termini, is what that is known as. And so the first proton to be lost is going to be right there. The next proton that can be lost is from the N termini. So this is our amino acid backbone. Ultimately, when you put those two groups together on one molecule, you're going to have a titration curve that looks a little bit like this. Now, I'm going to go with one more question. It should be open. I'm putting a 60-second timer on it. The phone number, text 1373 plus your response to 315-636-0905. So my question, it does show that it's open. Okay, we got some responses rolling in. It's great. We've got about 35 seconds left on it. Oh, is this one? Oh, okay. Well, thank you for mentioning this, Andrew. See, those are private messages, so I appreciate that. And um, looks like there was only, I'm sorry about that, the question type. Okay, so possible answer options. So people selected +1 or 0. I'm sorry about that, everyone. Um, so could ammonium adopt a -2 charge? Ammonium could not, and ammonia, ultimately, that could not be -2, could it be +2? No, it couldn't. It could either, this molecule can either be a +1 or 0. Now, with that in mind, that is the backbone for every single amino acid. So here are our 20 proteinogenic amino acids. And let's see, I'm going to go ahead and close that. That's a great question. So when we look at question of why couldn't it be +2, essentially, if we look at ammonium, where the a fair question for that would be, where would the second proton go? We have, you know, nitrogen rolls in, and what nitrogen brings to the table is it brings five valence electrons. So nitrogen, well, when it brings those five valence electrons, that's nitrogen with a formal charge of zero because it brings in five valence electrons. It has five that are basically assigned to it, and then three that are shared. Now, right here, nitrogen sees eight electrons, so it has a complete octet. Now, its formal charge is going to be plus one. It couldn't take on an extra bond because then it would exceed the octet rule. Now, when it comes to our protein-genic amino acids, these are the 20 structures. What I want you to recognize about this is we've got the same backbone for every single one of them. Now, go ahead and add to the chat. Um, what pH do you think that I displayed these molecules at? And I'm looking for a number. Um, let's go with 1, 7, or 14. Do you think this is a pH of 1, 7, or 14 is my curiosity. I got to vote for 1. I got to vote for, yeah, it's 1. The reason that it's 1 is because every single one of these groups is protonated. So if we look at the N termini of alanine here and the C termini of alanine, these groups are both fully protonated. And what that means is that there's a very high concentration of protons in the environment. Every place that a proton can go, it is already occupying that place. So we've got alanine, where this nitrogen has three bonds plus a nitrogen carbon bond, and that adopts a positive charge. Then we've got this end of our molecule that has, well, it has a proton as well, and it is neutral. So every single one of the molecules on here is displayed with a charge of, or sorry, with at a pH of effectively 1 at an extremely low pH. So these are all in solutions where there's a very high concentration of protons or hydronium ions. Now, with that said, if you look up, I bring that up because in different sources, you'll find different kind of presentations of amino acids. Sometimes you'll show them at a pH of 7, sometimes at a low pH. I think that this is most effective because you kind of remove some of the variation. Your N termini, your amino group, and your carboxy group are all protonated. Now, what that means is as these are placed into a slightly more basic environment, all of these groups are going to follow the same thing. And that is they're going to be deprotonated at this end. And then once they're deprotonated at the C termini on their carboxyl group, slowly but surely, they will then be deprotonated at the N termini. Now, when it comes to learning your amino acids and being able to identify these structures, there are some folks who look at it and they say, okay, there's 20 molecules. I need to know those 20 structures. And you do. For exams that I give you and quizzes and work that I give you, I will ask you to display them as um, looking at them. Sorry, I'll ask you to be able to identify approximately what pH they're displayed at. Now, I think that an effective way to learn the amino acid structures is to look at them and begin kind of breaking them down. So taking that group of 20 proteinogenic amino acids, taking that group and breaking it down a little bit and simplifying it for yourself. So here, what we have are two major categories. We have amino acids categorized as polar and as nonpolar. Now, one of the things that I want you to understand about this, and that's important to understand, is when it comes to these designations as polar or nonpolar, we're not asking about the backbone. We're simply asking about the R group. So, what is the polarity, or what is the kind of functionality? What types of charges can the R group adopt? Now, what that means is you can take this group of polar amino acids displayed here and break that group down a little bit. In addition to that, you can look at your nonpolar amino acids and break that group down a little bit. So we have a total of 11 amino acids that are classified as polar. We can take that and say, all right, well, rather than it being 11 amino acids, we can say three of them, lysine, histidine, and arginine, are our polar positive amino acids. Aspartic acid and glutamic acid are our polar negative amino acids. For our non-polar amino acids, we can look at those and say, okay, well, we've got a total of seven that are non-polar, and then we've got these two, and then that we'll classify as aromatics. But then we also have tyrosine. Tyrosine is a polar aromatic amino acid. So we have these different designations and different classifications because of, well, that's what the R group is capable of doing. Now, these definitions, I'm going to bring this up, and this is really important. If you look at, say, lysine, histidine, and arginine, which actually I'll jump ahead here. If you look at your polar negative amino acids, you have aspartic acid and glutamic acid. Now, it's a fair question to ask, why are these designated as negative? And the answer to that question is because these two groups and this definition, they are going to be negatively charged R groups at a physiological pH. So at a physiological pH, these amino acids will have an overall negative charge. Now, our positive are our polar positive amino acids, lysine, histidine, and arginine. Well, these will all have a positive charge at a physiological or a neutral pH. So understanding that is important. Did anyone else get disconnected? Um, no, I don't. So then when it comes to learning our amino acid structures and learning our names and being able to identify and kind of the jargon associated with amino acids, there's a very important person that we need to reflect on. And that person is a woman by the name of Margaret Oakley Dayhoff. Now, Margaret Oakley Dayhoff was a biophysicist and a bioinformatician back in the 1950s, and then concluded her career in like the late 70s, early 80s. And what she did was she studied protein folding. So she studied how proteins would assemble and what they would look like in three dimensions. And so she was doing these pretty complicated calculations about free energies of proteins. And what she was doing was she was like, okay, well, as we identify a protein, when we're trying to put together the sequence of a protein, writing out the sequence, saying, proline followed by an alanine, followed by a histidine. And if this is a protein that's 350 amino acids long, it would be cumbersome to say the least. And so what she said and she proposed and the work that she did led to simplifying that. Rather than using the full names of amino acids, she put together kind of guidelines that would lead to the formation and the production of three-letter codes and one-letter codes for amino acids. Now let's look back at the three-letter codes. There are some guidelines that were used for putting together the three-letter codes. Now, this is kind of an open-ended question. So can anyone add to the chat, looking at the full names and the three-letter codes, kind of a rule or an idea for some of those three-letter codes? And, this is just try to put together like one rule that would be perfect. The first three letters. Okay. The first three letters of the full name. That's a great place to start. Okay. Now let's go through and see if which ones that works for. Okay. So if we got aspartic acid, good. Glutamic acid, good. Lysine, good. Histidine, good. Arginine, good. Serine, three. Oh, here's one. Asparagine, glutamine, tyrosine works. I'm going to circle the ones that it doesn't work for. Good. Good. Okay, so of our 20 proteinogenic amino acids, this naming strategy works for 16 of those. So when it comes to, oh, I got to learn the three-letter codes for every amino acid, I mean, as long as you can begin spelling that name or read that name, you've got 16 of them down. So that's a good place to be in. Now, I want to look at asparagine and glutamine. Okay. What I'm going to do is I'm going to jump back and I'm going to show you these right here. Okay. So asparagine right here and glutamine right here. These are both polar, what are known as polar uncharged amino acids. Now, the significance of these two amino acids is that, well, asparagine is very similar in structure to aspartic acid. What is the difference between, or what is the functional group that's found on the R group of aspartic acid? Aspartic acid has a carboxylic acid, right? Now, in place, so if we look at aspartic acid, here's our carboxylic acid. Now, if you compare the name aspartic acid or aspartate and asparagine, first question is aspartic acid and asparagine, do those names sound somewhat similar to one another? Do they start with the first three letters that are identical? Yeah. Okay. So when we look at asparagine versus aspartic acid, how would you describe the difference between the functional group on aspartic acid and asparagine? I'm going to erase my writing there. Basically, what atom is present on the R group of asparagine that's not present on aspartic acid? One has a carboxylic acid, the other one has a ketone. Well, we've got that we've got that amine. Exactly. So asparagine is basically the aminated aspartic acid. Glutamine. Okay, let's look at glutamine. We've got one CH2, two CH2s, and then we've got that same kind of aminated carboxylic acid. So the nitrogen is our atom that's really different. Now let's go back and look at our three-letter code for asparagine and glutamine. Well, we have AS, which is the first two letters, and then we've got an N. GL, first two letters, and then an N. So glutamine, and then that suffix INE in terms of the name, and asparagine. Well, that's a result of this being basically the aminated version of aspartic acid and glutamic acid. So the proposal when it came to the rules for the first three letters was basically, or the three-letter code, it was basically, well, what are the first three letters? Can we use those? And for 16 of those 20 proteinogenic amino acids, the answer is yes. Then they basically came up with, okay, well, how can we modify that and make it kind of equally simple? That's how they came up with asparagine and glutamine. They are the aminated version of aspartic acid and glutamic acid, respectively. So if you can basically what I want to convey is if you can draw aspartic acid, then you can draw um, asparagine because all that you're going to do is replace one of those oxygens with an amine group. Now, isoleucine and tryptophan. Well, isoleucine, the decision was to not use ISO because ISO, I mean, that's a suffix in so many different molecules that that three-letter code would definitely be confusing. So then they dropped the ISO and instead went with the next total letters, ILE. Now, tryptophan, well, that's a little bit tricky because TRY, well, it's not being used by anything else, but that makes a word. TYR does not make a word. So that was part of the rationale that's highlighted in this paper from 1966 that IUPAC had a publication that was here's the new rules. Okay, now when we go on to look at our single letter codes, or does anyone have any questions about the three-letter codes? Is used twice, isn't that good?
Yeah, I remember so. This is what I got.
Did I? Oh,
What would you get, Terry?
I'm so sorry.
Yeah,
TR tripped. I'm sorry about that. Thank you for mentioning that. I was very confused. Tryptophan is TRP. Thank you, Andrew. Okay. So I apologize for that, everyone. Let me make that correction. I'm so sorry about that. I will correct that and re-upload the PowerPoints. Okay, so now on to our single letter codes. Does anyone have any questions about the three-letter codes before I proceed?
Well, I did it again and I got the mid migration.
Okay.
Yeah.
So our single letter codes,
Oh.
essentially we have 20 proteinogenic amino acids. We've got 26 letters in the alphabet. And so this was just the matter of, well, let's go ahead and go with, and actually go ahead and try to propose a rule similar to what we did right in the previous slide. Um, what do you think the rule would be for our single letter codes, looking at all of these options? Are there any common themes for our single letter codes?
You want me to stop sharing? Did you get it?
So first letter, single letter code, but you're absolutely right, Morgan. Doesn't work for every one of them. Now, if we go down the list, pretty quickly we run into redundancies or something that seemingly doesn't make any sense. Now, the rationale for lots of these was just to, well, let's use the first letter of the amino acid and we'll go from there. Okay, so that gives us basically, 8 to 10 of them. There are, however, ones that don't really make a lot of sense. Now, the rules that were followed was if there is a redundancy, if there's something that's used more that a single letter code is, or sorry, the first letter is the exact same, then we got to go on to a second rule. And the second rule would be to use phonics. So use the phonetic pronunciation of an amino acid's name and build from there. Now, we'll highlight this first one, aspartic acid. Okay. Well, if we think about that, if I'm pronouncing the word aspartic, the strong consonant there is a T. Well, T is already taken, so we couldn't use that. But if you pronounce it slightly differently, you arrive at aspartic, in which case that's where that letter D comes from. That first letter is because of the pronunciation of it. After that, glutamic acid gets an E. Well, there's not really a pronunciation of glutamic acid that gives you any insight into it being the letter E, but rather what we can do is we can look at the structures of these two amino acids. Aspartic acid and glutamic acid are almost the exact same molecule. The only difference is that glutamic acid is a little bit longer. There's one additional CH2 here. So that functional or that slightly longer functional group is where that rationale came from. It's almost like a sequence. So if aspartic acid gets D, then glutamic acid gets an E. Now, F for phenylalanine. Okay. Phonetic pronunciation, that works there. Now, K for lysine. Okay, well, if you look at the first three letters of lysine, L is in use as a single letter code, Y is in use as a single letter code, and S is all in use in a single letter code. And so K was basically the almost odd man out, or one of the odd man out. So that's how they arrived at K. Asparagine and glutamine got N and Q respectively. Now, Q for glutamine, that goes back to pronunciation. So Qtamine, that's one of the mnemonics that people use to remember amino acids and their single letter codes is they'll say, oh, glutamine is the cutest or Qtamine is the cutest amino acid. So Q. N is a um I think that ended up in a similar fashion as lysine, where it was available. Arginine, the phonetic pronunciation of arginine. Tryptophan, W. That seems kind of like an oddball, but if you look at the structure of tryptophan, which is right here, it is one of our aromatic amino acids. When you look at the structure of tryptophan, you have this bicyclic ring structure. So here is a W that basically you can draw when you look at that structure. So that's how it was given that W. Tyrosine, Y, that's again kind of the phonetic pronunciation and the availability of that single letter. So when it comes to three-letter codes, um, it's the first three letters except for basically four or five oddballs. The single letters, it's almost all, or it's not almost always, but it's frequently the first letter, but then there are some exceptions. Do we have to memorize the one letter codes? Yes, I want you to know the one letter and the three letter codes and kind of go in between these different variations. Okay, so that's because whenever you talk about a protein structure, you will list it as A, F, R, G, L. This would be a peptide that is read from this end. Alanine, phenylalanine, arginine, glycine, leucine. So that's kind of like being in the know of identifying protein structures. Now, to look at our positive and negatively charged amino acids again, this is a breakdown of what they are. Lysine, histidine, and arginine are your positive residues. Glutamic acid and aspartic acid are your negatively charged residues. Your nonpolars are proline, glycine, and leucine, and valine, alanine, isoleucine, as well as methionine. Tryptophan and phenylalanine are both classified as aromatics, but they're kind of under the big umbrella of nonpolar. So they're aromatic nonpolar residues. Now, in addition to those, well, tyrosine is also an aromatic residue, but it's a polar aromatic. How is it polar, or why is it classified as polar? Because it has this little hydroxide group on that six-membered ring. Other than that, serine, asparagine, threonine, glutamine, cysteine are what are known as your polar uncharged. So this is a distinction where it's important to distinguish your polar positive and polar negative from your polar uncharged amino acids. Now, when it comes to terminology associated with your amino acids, I'm going to give you this is takes you back to organic chemistry for a minute. I've got another top hat question that I want to share with y'all. I'm going to switch my share so that you can see it. So, what is the term for the carbon adjacent to a carboxyl group? Give it another 20 or 30 seconds with that.
It's not for me, I love organizing.
Okay. Looks like we are. I'm going to close this one. Responses. We've got awesome. 47 folks said alpha, and you're absolutely right. That's one of the reasons that you'll commonly hear of your amino acids referred to as your alpha amino acids. I always try to use the term proteinogenic amino acids because when you think about the term amino acid, well, that's any molecule basically that has an amino group and a acid. So there are beta amino acids, there are gamma amino acids. And these are important, significant molecules because of the fact that they can be involved as secondary metabolites. They can be involved in any number of functions beyond just as a part of a protein. Our alpha amino acids is in reference to this carbon right here. This is our alpha carbon. So that alpha carbon is where everything comes off of that. Now, you've possibly heard of beta branch amino acids. That's in reference to molecules like isoleucine. So here is our beta carbon. Is it true that difference between a polar molecule and a nonpolar would include the presence of hydrogen bonding? So the availability and the possibility of hydrogen bonding is your major distinguishing factor between something that can be classified as polar or nonpolar. That's a great private question that I just got. So here's our beta carbon, and isoleucine is a great example of a beta branched amino acid. Now, we'll refer to these all as alpha amino acids and proteinogenic amino acids. What I want you to know is I want you to be able to identify these structures. This will be included in the learning objectives that I'm going to post by the end of the day today. But learning these structures is very important. Now, my recommendation is try to classify them, try to group them and understand, okay, what this one is versus this one. These are my polar amino acids because this is the types of interactions they can be involved in. If we look at our non-polar amino acids, even something like methionine, for instance, that's always one that throws a little bit of a loop at people because they're like, oh, there's that sulfur. Well, despite that sulfur, the molecule is predominantly hydrocarbons. And so, what types of interactions are these non-polar residues going to participate in? They're going to participate in lots of hydrophobic interactions. And if not hydrophobic interactions, van der Waals interactions. Your polar amino acids, they love to form hydrogen bonds. They love to form ionic interactions. Now, one thing that I want to stress to everyone is asparagine and glutamine. These are two amino acids that are never going to be positively charged. So this group right here, this functional group, what people I've noticed over the years is they like to see this lone pair of electrons on that nitrogen and say, aha, I can put a hydrogen there. But no, you cannot. So that would not be a positively charged amino acid. So don't fall into that trap. Now, with all that in mind, what we're going to begin looking at on Monday is we're going to look at ionization. And we talked about it a little bit with respect to the ammonium and the acetic acid as models. Now, what we're going to do is we're going to put this together and look at our positively charged amino acids, our negatively charged amino acids, look at what those things will look at like, and calculate a PI. A PI is also known as an isoelectric point. An isoelectric point, by definition, is where a molecule has a zero overall charge. Does it have charges? Yes, it does. But those charges, if it's a positive and a negative, well, they'll cancel out, and the number of them will cancel one another out. So we're going to look at that on Monday, and we're going to start talking about drawing peptides as well. What does a peptide look like, and how do peptides vary in terms of their ionization? With that in mind, does anyone have any questions before I stop my share and stop the recording?
I know, like,
Um, well then, I presume that if somebody might be typing, and that's go for it. If there are no questions that anyone would like to ask, I hope you have a great weekend. I will see you again on Monday morning. Um, we'll be working through some more stuff with respect to our amino acid structures and drawing them and visualizing them as entire molecules. Expect the learning objectives later today, and I hope that will help you on preparation for the next exam. And yeah, if there's anything I can do to help you understand this material or help you kind of strategize for what your ultimate education goals are with this information outside of this class, please let me know. I would want to help and I can answer the questions that are asked. Okay, well, I'm going to stop my recording and